Hello and welcome back, everyone. We are on Lecture 7 in Fundamentals of Inorganic Gases. We are in the third out of 3 lectures in Chapter 3. So today we are covering the kinetic theory of glass formation. If you recall, over the past couple of lectures, we have covered other theories of glass formation in Chapter 3. We started with the structural theory, specifically Zachariason's random network model. From there, we went to Phillips's topological constraint theory. Now, Zachariason's model was kind of made in the context of oxide systems. Phillips proposed his topological constraint theory in the context of chalcogenide systems, or covalently bonded glasses. But what we're going to do today with the kinetic theory of glass formation is to present the most general theory of how we obtain glasses from the liquid state. One thing that you'll note about today's lecture is that it really doesn't depend on any specific chemistry. There's no mention of any specific glass structures. This approach is based on how well we can suppress crystallization in a glass-forming liquid, because suppressing crystallization is the key to being able to get the glassy state. So according to the kinetic theory of glass formation, any liquid can be vitrified, meaning any liquid can be cooled into the glassy state if that cooling occurs sufficiently fast to avoid crystallization. Now, the key thing in the kinetic theory of glass formation is that crystallization involves 2 steps. First, there is nucleation, and that is followed by crystal growth. Nucleation is where you have the first precursor to the crystal starting to form within the liquid matrix. And once that stable nucleus forms, it can grow into a crystal through the crystal growth process. Now, because there are 2 steps, and these 2 steps must occur in this order, first nucleation and then crystal growth, this means that in order to avoid crystallization, the system needs to avoid either one of these steps or avoid both of the steps or reverse the order of the steps. So it has to be nucleation first and then crystal growth in order to get crystals. And so that means we can suppress either one of them or simply change the order that those processes want to occur. Now, the following steps are needed to determine whether a system will form a glass or if it will crystallize. First, we need to calculate the rate of nucleation as a function of temperature. This is going to give us the number of nuclei that form per unit volume, per unit time. Next, we need to calculate the rate of crystal growth as a function of temperature. And then finally, we need to combine these 2 rates, nucleation followed by crystal growth, to determine the volume fraction of the system that crystallizes. And the combination of these 2 steps are included in this equation known as the Johnson-Mehl-Avrami equation. So what we're going to do in this lecture is to go through exactly these steps. We're going to start with getting the nucleation rate, then we're going to go to the crystal growth rate, and then finally we're going to obtain the volume fraction of crystallization using the Johnson-Mehl-Avrami equation. First, what is nucleus? In this context, a nucleus is a precursor to a crystal. It is a periodic assemblage of atoms without recognizable crystal growth habit planes. In other words, this is kind of the smallest cluster of atoms that start to show some sort of crystalline order, but where you can't really determine recognizable crystal growth planes at that point. Now, once a stable nucleus forms, it grows into a crystal. And a crystal is an assemblage of atoms in a regular periodic array with recognizable growth habit planes. Nucleation, this first step, occurs because the atoms are constantly vibrating in the liquid state and moving around as a result of thermal energy in the system. So if a nucleus forms, it's really forming kind of by chance because of these random vibrations that occur in the liquid state. Now, the nucleation rate is typically denoted here with a capital I. And suppose that every atomic vibration in the liquid allowed an atom to join a nucleus. If that were true, then the nucleation rate I would simply be equal to this n, which is the number of atoms per unit volume multiplied by the vibrational frequency of the atoms. If this were true, then this would tell you that every single vibration in the liquid leads to the formation of a nucleus, and that nucleation rate, meaning the number of nuclei that are formed per unit volume per unit time, would be given by simply the product of this number of atoms per unit volume, which is the number density of atoms, multiplied by the vibrational frequency, or how many times per second that the atoms are vibrating. However, there are two barriers to accomplishing nucleation, and those barriers in practice significantly lower the nucleation rate compared to this ideal nucleation rate shown here. These two barriers are called the kinetic barrier and the thermodynamic barrier. The kinetic barrier is here denoted as delta E sub D. This is the activation energy required for an atom to cross the liquid nucleus interface. This involves most likely the breaking of bonds with nearest neighbors and some realignment into the more ordered structure within the nucleus. The thermodynamic barrier is denoted here as W star, and this is the net free energy change in the system as a result of forming a stable nucleus. And when we account for these two barriers here, we are multiplying this ideal nucleation rate, or this maximum nucleation rate, n times nu, times two Boltzmann probability factors, e to the minus and then the barrier, either the thermodynamic barrier here, W star, or the kinetic barrier, delta E sub D. And those are divided by the available thermal energy of the system, which is Boltzmann's constant K, times the absolute temperature of the system, T. And always make sure, of course, that your temperatures are expressed in units of Kelvin for anything to do with thermodynamics or kinetics. So if you've got the ratio of the barrier over KT, this is telling you kind of what is larger. Is your barrier larger, or is your available thermal energy larger? And then e to the minus, that quantity, e to the minus barrier over KT, is the Boltzmann probability factor. This is the probability of actually overcoming that barrier given a vibration. So when we put this together, n times nu, this is the maximum nucleation rate. Little n is the number of atoms per unit volume. Those atoms are vibrating at a frequency of nu. So this is telling you how many times per second that the atoms are vibrating. Every one of those vibrations is like an attempt to overcome these two barriers. Every vibration is like an attempt to overcome both the thermodynamic barrier, W star, and the kinetic barrier, delta E sub D. The probability of that vibration overcoming one of those barriers is e to the minus barrier over KT. And what we need to form a stable nucleus is the probability of overcoming both the thermodynamic barrier and the kinetic barrier. And so that means it's a product of both probabilities, the product of the probability of overcoming the thermodynamic barrier times the probability of overcoming the kinetic barrier. And if we successfully overcome both of those barriers, that gives us the actual nucleation rate here, I. So that's where this equation comes from, the maximum nucleation rate multiplied by these probability factors of overcoming both the thermodynamic and the kinetic barriers. And so what we're going to do now is let's take a closer look at this barrier. And we're going to consider two different cases for the thermodynamic barrier, homogeneous nucleation and heterogeneous nucleation. These are the two broad types of nucleation that can be defined. Homogeneous nucleation is the chance assembly of a number of atoms to form a group that leads to the lowering of the net free energy of the system. The probability of such an assembly is equal everywhere throughout the material. It's homogeneous because this is the same rate throughout the liquid. On the other hand, heterogeneous nucleation is the chance assembly on some sort of pre-existing surface or interface. So for example, if you've got a liquid that is in some sort of a container, Within the bulk of the liquid itself, the nucleation that it experiences would be homogeneous nucleation. However, at the interfaces between the liquid and the walls of the container, that could exhibit heterogeneous nucleation, where the heterogeneous nucleation rate might be faster compared to the homogeneous nucleation rate in the bulk. Also, at the free surface, the surface between the liquid and the air, that could also be a location for heterogeneous nucleation to occur. So we're going to deal with the case of homogeneous nucleation first, since that is the simpler case, and then we're going to go to heterogeneous nucleation. So starting with homogeneous nucleation, how is it that we determine the thermodynamic barrier for homogeneous nucleation? What we need to do is consider the change of the Gibbs free energy of the system as a result of forming a nucleus of a different size. And what we're going to do is consider that there are two terms to this change of free energy, and we're going to assume that the nucleus is spherical in shape. So the change of the free energy of the system, delta G, this change of the Gibbs free energy, is equal to the summation of two terms. The first term here is a volumetric term. This is 4/3 times pi times r cubed. That is the volume of the nucleating cluster. So this is just the equation for the volume of a sphere of radius r. And that volume is multiplied by delta G sub x. Delta G sub x is the change of the free energy of the system as a result of forming a nucleus. The subscript x is indicating a crystal, and this is the change of free energy per unit volume of crystallizing. So if we have this change of free energy per unit volume, delta G sub x, multiplied by the volume that becomes a nucleus, that gives us the volumetric contribution to the free energy change. So this first term is the volumetric term, and if we plot this, the change of free energy here on the y-axis versus the radius of the nucleus r on the x-axis, this delta G sub x is going to be a negative quantity for any temperature below the melting point or below the liquidus temperature of the system. Because at those lower temperatures, if the liquid is in the supercooled liquid state, which means that the temperature is below the temperature at which crystallization is thermodynamically favorable, the fact that crystallization is thermodynamically favorable means that the change of free energy due to crystallization must be negative. A negative free energy is more thermodynamically favorable. That's telling the system that it is thermodynamically favorable to crystallize. So this quantity here, delta G sub x, is negative at any temperature below the liquidus temperature. And when we multiply that by 4/3 pi r cubed, we get this cubic dependence here of a net decrease in the free energy of the system. And that is what is plotted here as the green curve. So this green curve here is just the contribution to this first term of the change of Gibbs free energy. Now, the second term is the surface energy contribution to the change of Gibbs free energy. This is 4 pi r squared times gamma. This 4 pi r squared is the equation for the surface area of a sphere of radius r. And then gamma is the surface tension. The surface tension is just the change of Gibbs free energy per unit area as a result of forming an interface between two different species. So the reason that we have to include this term is that if we are forming a nucleus within a liquid matrix, that's also forming an interface between that nucleus and the liquid matrix. And at that interface, the atoms are misaligned because in the liquid state, in the liquid matrix, the atoms want to be in a disordered configuration. But in that nucleating crystal cluster, the atoms want to be in an ordered configuration. And so there's a mismatch between the bonding within the crystal, within that nucleating crystal, and within the liquid matrix itself. That mismatch in bonding means that there's a free energy penalty that needs to be paid as a result of having that interface. And therefore, this is a positive contribution to the Gibbs free energy because it is thermodynamically unfavorable to have one of these interfaces. Gamma is a positive number, and of course 4 pi r squared is also a positive number. And so the surface energy contribution is plotted here as the blue line, 4 pi r squared gamma. So we have a positive contribution to the Gibbs free energy, which is a result of forming this interfacial area. And then, so that is the blue line. And then there's a negative contribution to the free energy, which is given by the green line. So this volumetric term says that, yes, forming a crystal nucleus is thermodynamically favorable. This is something that the system wants to happen. But the surface energy term, which is positive here, says that it is unfavorable. So the question is, which one wins? What we need to do is add these two terms together. So we add the volumetric contribution to the free energy change to the surface area contribution to the free energy change. That is the equivalent of adding this blue curve to the green curve. And when we add them together, we get the black curve shown here, which is the total change of the Gibbs free energy of the system. And what we see is that at small values of R, the surface area term is the dominant term. This blue curve is increasing at a rate faster than the green curve is decreasing at these very small values of R. And this makes sense because if you have a sphere, if you get a very tiny sphere that starts to form, the surface area is a pretty large fraction of that sphere, right? And so for very small spheres, the surface energy term is dominant over the volumetric term. However, as that sphere grows, the surface energy becomes less and less important compared to the volumetric term. That's because the volumetric term has an r cubed dependence and the surface energy term only has an r squared dependence. So as we get to larger sizes of the sphere, or in other words, larger values of r, the green curve here, this volumetric term, starts to become dominant compared to the surface energy term or this blue term. So if we add these two curves together in this initial region here, going from 0 up through this maximum, this region here is where the surface energy is dominant. However, beyond that maximum, this is where the free energy starts to decrease with increasing R. And this is where the volumetric term starts to become dominant. So this location of the maximum here is known as R star. R star is the critical size of a nucleus in order for it to become stable. Why is it that a stable nucleus corresponds to the maximum here? We can understand this if we consider what is the direction that the nucleus needs to change in size in order to lower the free energy of the system. If we have any nucleus that has a size that's greater than this critical nucleus size of R star, so anything that is to the right of this maximum, how is it that the free energy of the system is lowered at that point? So here, if we want to lower the free energy of the system, anywhere to the right of this dashed line, we would lower the free energy of the system by increasing the size of the nucleus. In other words, by going to larger values of R, because if we go to larger values of R, the free energy of the system is decreasing. So we know that this is a stable nucleus because it wants to grow, because by growing the nucleus, this can lower the free energy of the system. On the other hand, suppose that we are on the left-hand side of this vertical dashed line, or in other words, suppose that we have a nucleus that is R less than R star. In this region, how do we decrease the free energy of the system? We would decrease the free energy of the system by moving to the left, which means by shrinking the nucleus and making it disappear. Because in this region to the left of R star, so for R less than R star, this is where we are dominated by the surface energy term, which means that we want to minimize the surface energy contribution to the free energy. And the way to do that is to shrink the nucleus until it disappears and goes away. So any nucleus that is a size less than R star is an unstable nucleus. What we are concerned with mostly is what is the likelihood of forming a stable nucleus with R greater than R star. So it becomes, very important to then determine what is this value of R star. How do we determine this? We know from calculus that the way to find the location of a maximum like this is to take this algebraic expression for our total Gibbs free energy change, so the volumetric term plus the surface energy term, and then we need to take the first derivative of that with respect to R, and then set that first derivative equal to 0. Where that derivative is equal to 0, that gives us the R star. And if we know the value of R star, then we can plug it back into our equation to get this change of Gibbs free energy that is associated with R star. And that is W star. That is a thermodynamic barrier for nucleation. This is the work that is required to form a stable nucleus, W star. So what we need to do is take our expression here and take the first derivative of that with respect to R. And that's what we're going to do here at the bottom. The first derivative of this change of Gibbs free energy with respect to R is then equal to, we take this 3 here, bring that down so it's multiplied by 3. So the 3 cancels with the 3 in the denominator, and we have 4 pi r squared. The exponent goes down by 1, and then times delta g sub x. This is the first derivative of the volumetric term. Likewise, the first derivative of the surface area term means that we multiplied by 2, so it becomes 8 pi r times gamma. And we take this expression, which is our first derivative, set it equal to 0 to find the location of the maximum. There are actually 2 solutions to that. The trivial solution is R equals 0, which is actually this minimum here of the Gibbs free energy. This is just a trivial solution that we're not interested in. What we are interested in is the positive value of R that gives us this maximum. So what we need to do is find the other root of this equation. So we divide this equation by R and then solve for R, and that gives us the value of R star, which is equal to minus 2 gamma over delta G sub x. Remember that the gamma is a positive number, delta G sub x is a negative number, and so we've got this minus sign out in front that's multiplied by this negative number here, 1 over delta G sub x, and that means that the sign of R star, the algebraic sign, is positive. So R star is a positive number, and that corresponds to the location of this maximum. And it is just given by this simple ratio here between the surface tension, gamma, and the volumetric change of the Gibbs free energy. Now, if we take this value of R star, in order to get the value of the thermodynamic barrier W star, the work that is required to form a stable nucleus, we take this value of R star and we stick it back into our initial equation here. So this is our equation for delta G. We plug in R star equals minus 2 gamma over delta G sub x. And when we stick it back in here for R cubed, this equation here for R star gets cubed. We stick it in with the R squared part, and it gets squared. So we cube it, combine like terms here on the left and on the right, and then finding the common denominator here and combining these 2 terms, we see that the W star is equal to 16 pi gamma cubed over 3 times the square of delta G sub x. So again, this is expressed strictly in terms of the surface tension here, gamma, and the volumetric change of the Gibbs free energy, delta G sub x. So now we've got the expression for R star, which is the size of a stable nucleus, and we've got an expression for W star, which is the work that is associated with forming a stable nucleus, and that is the thermodynamic barrier for nucleation. That was for homogeneous nucleation. The next thing to consider is, what about heterogeneous nucleation? This is nucleation that occurs at a surface or interface, and the presence of a surface or interface complicates the geometry of the problem as well as the thermodynamics of the problem, because now, instead of there just being one relevant surface tension, there are actually three relevant surface tensions. There is the surface tension between the liquid matrix and this nucleating crystal cluster. This here is denoted as gamma Lx, L for liquid, X for the crystal cluster. This gamma Lx is the same as the gamma from the previous slide. It is the same as the surface tension that is used in the case of homogeneous nucleation, because this is the surface tension associated with the interface between the liquid matrix and the nucleating crystal cluster. But we have two other surface tensions we have to consider. If there is some sort of other solid substrate there or some other material that the nucleation is happening on top of, this substrate is denoted with a subscript S. There are two surface tensions associated with that. One is gamma Ls, which is the surface tension between the liquid matrix and the solid substrate, hence the subscripts Ls, liquid and substrate. And then we have the surface tension between the nucleating crystal X and the substrate here S, and that is the gamma XS. So there are three different surface tensions here between all pairwise combinations of these three different phases in the system: the liquid, the crystal cluster, and the solid substrate. So that gives us these three different surface tensions. And the total surface energy of the system then is taking each one of the surface tensions and multiplying by the corresponding area. So the surface tension between the liquid and the substrate here, gamma Ls, multiplied by the area of that interface, the area between the liquid and the substrate. That gives you the Gibbs free energy contribution of that particular interface. Then we add to that the interface here, the contribution from the nucleating crystal cluster X and the substrate here. So it's gamma XS times A XS. And then the same thing here for the interface between the liquid and the crystal. So if you add all three of these contributions, what you get is the total surface energy of the system as a result of those interfaces. And of course, the key parameter here is the contact angle theta. This contact angle here, theta, is represented by a force balance among all these three interfacial forces that are acting on the system. And we express this value of theta using Young's equation. And the way to think about Young's equation is that you've got some force here that's acting to the left, which is proportional to this gamma Ls here, this interface acting in this direction. We've got an interface acting in the opposite direction here, gamma XS. And then acting along this angle here with this angle theta, you've got the contribution of gamma Lx. And so the horizontal component of that would be gamma Lx multiplied by the cosine of theta. So the way to get Young's equation is you have a force balance. Everything acting to the left here is equal to everything acting to the right. So acting to the left, you've got gamma Ls, and then the forces acting to the right have contributions from gamma XS, and then gamma Lx, just the x part of that. So it's gamma Lx times the cosine of theta. And then you can use this equation known as Young's equation in order to solve for the contact angle. And this contact angle is really the key parameter that governs the interfacial thermodynamics when you've got a setup such as this. Now, for heterogeneous nucleation, the simplest way to solve for this is to assume that this nucleating cluster here is still spherically shaped, but just kind of the cap of a sphere, where you take a sphere and chop off part of it underneath. And so you just have this cap of a sphere on top. And if you assume that geometry and solve for the critical size nucleus to form a stable nucleus, R star, you get exactly the same size in heterogeneous nucleation as you do in homogeneous nucleation. So there's no difference in R star between homogeneous and heterogeneous nucleation. It's still equal to minus 2 times gamma Lx. So this is the surface tension between the liquid and the crystal phase, and that ratio over then delta G sub x, the volumetric change of the Gibbs free energy. What is different is the work of nucleation, the W star, which is the thermodynamic barrier for nucleation. The W star for heterogeneous nucleation is equal to this term here, which is the same as what we already obtained here for the work of homogeneous nucleation, W star homogeneous, multiplied by this geometric term, which depends only on the contact angle here, theta. So the size of the nucleating cluster is the same between homogeneous and heterogeneous nucleation, but the work of nucleation is different. And in fact, the work of heterogeneous nucleation is equal to the work of homogeneous nucleation multiplied by a geometric term that depends only on the contact angle theta. So what are some limiting behaviors here of the work of heterogeneous nucleation? Let us consider first, what if we have the limit of a perfectly wetting substrate? If you have a perfectly wetting substrate, this is the limit of the contact angle going to 0, where this nucleating crystal cluster would perfectly wet the solid substrate. And in that case, that corresponds to a theta equals 0. And if you put in a theta equals 0 here, the cosine of 0 is 1. So you'd have a 1 minus 1, which is 0, which means that in the limit of a 0 contact angle, the thermodynamic barrier for nucleation disappears, and all that you have left is the kinetic barrier for nucleation. So in this limit of contact angle going to 0, the W star for heterogeneous nucleation is equal to 0. Now, if we look at the opposite limit here, if you've got a perfectly non-wetting substrate, a perfectly non-wetting substrate would be a contact angle of 180 degrees. So this would be just your perfect sphere sitting on top of the substrate, but not wetting it at all. So it's not really interacting with that substrate at all. And if it's not interacting with the substrate at all, it's the same thing as if that substrate weren't there. And so if you plug in 180 degrees into this equation, this geometric term here on the right becomes 1. And when that becomes 1, then the heterogeneous work of nucleation is equal to the homogeneous work of nucleation. So for a perfectly non-wetting substrate, it's as if the substrate isn't there. And the thermodynamic barrier for heterogeneous nucleation is the same as that of homogeneous nucleation. However, if you take the other limit of a perfectly wetting substrate, then the thermodynamic barrier disappears. And of course, for contact angles in between 0 and 180 degrees, there's a continuous variation here of the work of forming a stable nucleus between 0 and the homogeneous case. So what does this mean? Is if we have a perfectly wetting substrate that eliminates the thermodynamic barrier for nucleation, this is a case of what's called oriented overgrowth, or more generally called epitaxial growth. And this is like if you purposely want to grow a crystal in a liquid, what is the most effective way to grow a crystal in a liquid? It would be to seed that liquid with exactly the crystal that you want to grow. So if you've got liquid silica, and let's say that you want to grow quartz out of it. If you want to grow a quartz crystal in liquid silica, the most effective way to do it would be to actually take quartz crystals, put them into the liquid silica, and those quartz crystals then mean that nucleation is no longer required because it could just build and grow that crystal that is already present. And there's no thermodynamic barrier for that to happen because all of the atoms that grow in the crystal are already perfectly aligned with it. If you don't seed it with exactly the crystal you want to grow, you could seed it with another crystal that has a very similar crystal structure to the one that you want to grow, and that likewise would dramatically reduce the thermodynamic barrier for nucleation. Now, one of the assumptions that is also made here in this, what we're doing is classical nucleation theory. One of the assumptions is to assume that the two contributions to the Gibbs free energy, to this change of delta G here, that is the change of enthalpy, delta H, and the change of entropy, delta S. It's often assumed that the delta H and the delta S do not change with temperature, at temperatures near the melting point or near the liquidus temperature of the system. So if we write the change of Gibbs free energy here, delta G equals delta H minus T delta S. If delta H and delta S are both constants with respect to temperature, what that means is that we can take the temperature derivative of this expression. This constant here, delta H, drops out. The delta S is a constant, and then you've got this minus T. And so the temperature derivative here is simply minus delta S. And if you take that and then integrate both sides of this equation from the melting point Tm to some other temperature T below the melting point, that is equivalent to the change of the Gibbs free energy of the system between the melting point Tm and this new temperature T. And this would just be equal to minus the change of entropy of the system minus delta S times that change of temperature. So that difference in temperature is T minus Tm. And this gives you, pretty good approximation for what that change of Gibbs free energy would be. So we can write this as the product then of the change of temperature, this T minus Tm as just simply delta T, and then flipping the sign of the entropy here. So this is an entropy of fusion, which is a positive number here. The change of Gibbs free energy delta G sub x can be approximated as the product of the temperature change of the system, which is a negative number for supercooled liquids, and the change of entropy, which is a positive number. So this product here gives us an approximation of delta G sub x. If we are at the melting temperature itself, if you are at T equals Tm, then this delta T goes to 0, which means that the change of Gibbs free energy is 0 at the melting temperature. In that case, then we can relate this entropy of fusion here, delta S sub F, to the heat of fusion or the enthalpy of fusion, delta H sub F, over the melting temperature of the system. So this would be a thermodynamically equivalent way to represent the change of entropy as a result of this phase change. For the reversible case, it is simply the delta H, the heat of fusion or enthalpy of fusion, divided by melting temperature. So this delta G sub x, remember, if we go back, we had an expression for our delta G sub x here, which was in terms of W star, the work of forming a critical size nucleus. So this is just another way of expressing this W star by, instead of expressing it in terms of delta G sub x, we can take this approximation for delta G sub x here and plug this into the denominator of that equation. And if we do that, we get this equation here for the nucleation rate. So I, the nucleation rate, this is the number of stable nuclei that form per unit volume per unit time. It's equal to the number density of atoms here, n, times the vibrational frequency, nu, times our Boltzmann probability factor using the thermodynamic barrier. And now this thermodynamic barrier is expressed in terms of all of these quantities. So it's 16 pi gamma cubed times the melting temperature squared over 3 times the heat of fusion squared times the change of temperature. And then also in the denominator, you have the available thermal energy of the system, kT. So this is one of the ways that the thermodynamic barrier for nucleation is expressed. Then, of course, we have the kinetic barrier, which is the same. So this e to the minus delta E sub d over kT. Now, what does this look like if we plot it? Now, if we were to plot now this rate of nucleation here on the horizontal axis versus the temperature on the vertical axis, what we see is that if you've got delta T equals 0, for delta T equals 0, that means that we are at the melting temperature, and the nucleation rate is 0 at the melting temperature because there is no thermodynamic driving force for nucleation to occur. So in this region, we are thermodynamically controlled, and if you lower the temperature below the melting point, this is where crystallization becomes thermodynamically favorable. But at very small temperatures below the melting point, the nucleation rate is still very small, and that's because the change of Gibbs free energy as a result of crystallizing is also relatively small. This is what's called the metastable zone of undercooling. Even though it is thermodynamically favorable to nucleate, in practice, there is a very low rate of nucleation because the thermodynamic driving force is still rather small. However, as we increase delta T, so if delta T becomes larger and larger, our thermodynamic driving force for nucleation becomes greater and greater, and that means that this nucleation rate is increasing as we lower the temperature because there is a greater thermodynamic driving force for nucleation. But what happens is that nucleation goes through a maximum, and then it turns around and starts to decrease as you lower the temperature even more. What's happening in this lower region is as the nucleation rate is decreasing with lower temperatures, this is because of the kinetic barrier. This is because the kinetics of the atomic motions are becoming slower and slower. And so in this lower region, everything below this maximum, where the nucleation rate is decreasing as temperature is decreasing, this is the kinetically controlled region. At everything that is above, at temperatures above this maximum point, this is the thermodynamically controlled region. So here, the thermodynamic driving force increases as you lower the temperature. When you get to this maximum here, that's where it starts to become kinetically limited, because at any temperatures lower than that, the kinetics becomes slower and slower, and that limits the rate of nucleation. So the temperature at which this maximum nucleation rate occurs corresponds to the ideal trade-off between thermodynamic and kinetic effects. This is where you've got a thermodynamic driving force that is still large enough for nuclei to form, at the same time that the kinetics are fast enough for it to occur. So if you want to maximize the nucleation rate, this temperature is where you get this ideal trade-off between thermodynamics and kinetic effects. If you want to minimize the nucleation rate, suppose if you want to form a glass and not have nuclei or crystals, what that means is that you need to cool as quickly as possible through that regime in order to minimize the amount of nucleation that occurs. All right, that does it for the nucleation part. The next step is crystal growth. So after we get the nucleation rate, the next step is to get the crystal growth rate. Once a critical size nucleus has formed, that means that we have formed a stable nucleus. So once a stable nucleus is formed where the size is at least R star, so R greater than R star, now the crystal growth may occur by advancing or depositing new atomic layers from the liquid onto this interface between the nucleating crystal and the liquid. So in other words, we're taking atoms from the liquid and incorporating them into the growing crystal. And the crystal growth rate depends on how rapidly atoms can diffuse from the liquid regions to that interface between the crystal and the liquid. Now, the kinetics of crystal growth was developed by Turnbull and Cohen, and what they did was to assume a simple kind of double well potential here, where you've got two free energy minima corresponding to two possible sites for atoms to occur. There is the crystal site here labeled X, and at any temperature below the melting point, the crystal has a lower free energy compared to the liquid. That's why this well here for the crystal is lower than the well for the liquid state here on the right, which is labeled L. The difference of free energy here is labeled as minus delta G sub X. And then that is one of the relevant energies that we need to consider. The other is this transition barrier here, which is what gives us the activation energy of going from the liquid state to the crystal state. So if you've got atoms here in the liquid, the atoms are vibrating in the liquid. In order to get incorporated into the crystal, they need to overcome this barrier to pass across the interface and then get incorporated into the crystal state. And the size of that barrier that has to be overcome is given by this delta E prime, which is the activation energy. So the frequency of having a successful jump from the liquid state to the crystal state is this gamma Lx. This is going from the liquid to the crystal, from L to X. This is equal to our attempt frequency, nu. Every attempt frequency is like every vibration in the liquid. Every vibration here in the liquid state is like an attempt to overcome this barrier. The probability of actually overcoming the barrier is equal to our Boltzmann probability factor. So that is e to the minus barrier over thermal energy that's available. So it's e to the minus delta E prime over KT. So every vibration is an attempt to overcome the barrier. The probability of actually overcoming the barrier is this exponential of minus delta E prime over KT. And so if you take the product of the two, that gives you the rate of successful jumps from the liquid to the crystal. However, atoms in the crystal are also vibrating, and every vibration within that crystal is like an attempt to overcome the barrier going from the crystal to the liquid, which, as you can see, is a larger barrier that's equal to the summation of these two. So if we're starting in the crystal state, overcoming this total barrier is equal to the delta E prime plus the negative delta G sub x. So in that case, the frequency of successful jumps going in the reverse direction from the crystal to the liquid is gamma XL. See that we've switched the order here of the subscripts because this is going from the crystal to the liquid, from X to L. This is equal to the vibrational attempt frequency multiplied by its Boltzmann probability factor. So nu times exponential of minus this larger barrier of delta E prime minus delta G sub x over KT. So this upper rate tells us the rate of going from the liquid to the crystal. This lower equation here tells us the rate of going from the crystal to the liquid. The next question is, what is the net crystal growth rate? The net crystal growth rate would be the difference between these two rates multiplied by how much that the crystal is growing for every atomic layer that's added. So if A, this little a, is equal to the distance of basically the length scale of when you add a new atom to the crystal, how much is it growing in a length sense, multiplied by this difference of the two rates. So gamma Lx minus gamma XL, this is all the atoms going from the liquid to the crystal, minus the rate going from the crystal to the liquid. The difference here gives us the net rate. We multiply that by our length dimension here of the atomic separation distance, and that gives us the crystal growth rate. And so when we take the equations here, so counting for these two equations for gamma Lx and gamma XL, we stick those into this equation. They both have a common e to the minus delta E prime over KT factor. That common factor gets pulled out in front. They both have a common vibrational frequency factor that gets pulled out in front. And then what we're left here is 1 minus E to the delta G sub x over KT. So this gives us then Turnbull and Cohen's expression for the crystal growth rate. Now, let's look at some of the interesting behaviors here. Suppose that you have a temperature that is above the melting temperature. If the temperature is above the melting temperature, then it's thermodynamically favorable for the crystal to melt and form a liquid. And if that's the case, the delta G sub x, the free energy of crystallizing, is positive because it's thermodynamically unfavorable for the system to crystallize if it's at a temperature above the melting point. And so if you put in a positive delta G sub x, the crystal growth rate is negative. This means that crystals will dissolve or melt at temperatures above the melting point. If you are at exactly the melting temperature, if you're at T equals Tm, then the Gibbs free energy of the liquid is equal to the Gibbs free energy of the crystal, which means that the delta G sub x is 0, and that yields a crystal growth rate of 0. If you take the limit of going to 0 temperature, so at very low temperatures, then the kinetic term is approaching 0, and you also have a crystal growth rate of 0. Now, there are a couple of modifications to Turnbull and Cohen's expression. One of them is called Wilson-Frankel theory, and this actually relates the expression here with this delta E prime to the diffusion coefficient of the atoms and the liquid. The underlying assumption here is that the barrier that governs diffusion, delta E sub prime, is the same barrier that governs the ability of the atoms to cross the interface between the liquid matrix and the crystal. So if it is the same barrier, the same kinetic barrier for diffusion as it is for crystal growth, then that means that the same barrier can be used in both expressions. And an expression for the diffusion coefficient, D, is simply the distance of each hop squared, so the interatomic spacing A squared, times the attempt frequency for diffusion, which is assumed to be the same as the vibrational frequency for crystal growth, multiplied by e to the minus delta E prime over KT. With that expression, we can take this, note that we've got an A nu e to the minus delta E prime over KT, this first part of our crystal growth expression, and write it now in terms of the diffusion coefficient D divided by A. And this gives us a modified form of this crystal growth rate, which is now expressed in terms of the diffusion coefficient. So this has effectively eliminated both the vibrational frequency nu and this kinetic barrier here, delta E prime, from the equation. And what we're left with is a thermodynamic parameter here, delta G sub x, and a measurable kinetic quantity, the diffusion coefficient of the atoms. So in many cases, this is often the simpler expression to use. One more step that can be taken is by relating the diffusion coefficient to the viscosity of the liquid matrix phase. And that can be done using the Stokes-Einstein relation, which relates the diffusion coefficient here to the inverse of the viscosity, 1 over eta. And in that case, we can take this expression here and recast it in terms of viscosity instead of diffusion coefficient. And now our crystal growth rate now is expressed in terms of viscosity, which is often an easier to measure quantity compared to the diffusion coefficient D, and then this thermodynamic factor. And in fact, this expression here is quite often used to get predictions of crystal growth rate, and it generally offers pretty good agreement between experiment and theory. This is an example that shows the calculated versus measured crystal growth rate of cristobalite from liquid silica. And what you can see here is that the rate is on the y-axis. This is the rate of crystal growth versus the temperature. The rate crosses zero here at the melting temperature of silica, which is 1737 degrees C, if I recall. The rate is zero here because there is zero thermodynamic driving force for crystallization, because the Gibbs free energy of the liquid is equal to the Gibbs free energy of the crystal at the melting point. If you are at temperatures above the melting point, the crystal growth rate is negative, and that's because the crystals are shrinking as they are melting. Because at these higher temperatures, the liquid is thermodynamically favorable compared to the crystal. But if you are at lower temperatures, the crystal growth rate is positive, because at lower temperatures, it is thermodynamically favorable for the system to crystallize. So the crystals will grow in a positive direction as atoms from the liquid get incorporated into the growing crystal. And what you see here is actually a very similar trade-off to what we saw in the nucleation case, where even for crystal growth, the crystal growth increases as you lower the temperature because there's a greater thermodynamic driving force for atoms to be incorporated into the crystal. This region here is the thermodynamically limited region. But when we hit this maximum here, this maximum is where you've got the ideal trade-off between thermodynamic and kinetic effects. This is where the maximum crystal growth rate occurs, and any temperatures below that is the kinetically controlled region. This is where the kinetics of overcoming that activation barrier become too slow, and at these lower temperatures here below the maximum, this is the kinetically controlled region. So the temperature at which the maximum crystal growth rate occurs is where there's this ideal trade-off between thermodynamic and kinetic effects. Now, at the very beginning, we noted that in order for crystallization to happen, it's a two-step process. First, nucleation has to occur, and then crystal growth has to occur. So if we take these two different rates, the rate of, in this case, homogeneous nucleation here, plot that versus temperature, and then plot the rate of crystal growth versus temperature, you get two curves here that both have peaks. The peaks occur at different temperatures. The peak here for this represents the maximum rate of homogeneous nucleation, which is the ideal trade-off of thermodynamic and kinetic effects for the nucleation process. The peak here for the maximum crystal growth rate occurs at a somewhat higher temperature. This is the ideal trade-off of thermodynamic and kinetic effects for the crystal growth process. And that typically occurs at somewhat higher temperatures. Now, if we have a liquid state here at the melting temperature, the crystal growth rate and the nucleation rate are both 0 at the melting temperature, since there's no thermodynamic driving force for either of those processes to happen. If you're at temperatures above the melting temperature, the nucleation rate is 0, but the crystal growth rate is negative because the crystals are melting at those higher temperatures. So if we want to form a glass, what that means is that we need to suppress crystallization, which means that we need to suppress either or both of the nucleation or crystal growth processes, or reverse the order of the two. So what we do is we start off with a liquid here at some temperature, at the melting temperature, let's say, and then we cool it. And as we cool it, it's going to see this crystal growth curve, but crystal growth can't occur because the nuclei haven't formed yet. But when you get to this region where nucleation occurs, that's where all these precursors to crystals start to form. These nuclei start to form. If you get stable nuclei, those stable nuclei can then grow into crystals. And this shaded region here is the region where both nucleation and crystal growth are likely to happen. This shaded region is the dangerous region if you want to form a glass, which means that you need to cool the liquid fast enough through this shaded region so that you minimize the amount of crystallization in the system, because this shaded region is where nucleation and crystal growth occur, which means that there's a net increase of the volume fraction of crystals. That net increase of the volume fraction of crystals is given by combining the nucleation and crystal growth rates, where first nucleation occurs, followed by crystal growth. And that equation that governs that for a constant temperature T is called the Johnson-Mehl-Avrami equation. The Johnson-Mehl-Avrami equation gives us the volume fraction of crystals that form. That volume fraction of crystals is denoted by the capital X. That is equal to the volume of crystals in the system, V sub X, divided by the total volume of the system, V. So this ratio here gives us the volume fraction of crystallization. And if we hold the system at constant temperature so that there's a constant nucleation rate I and a constant crystal growth rate U, and considering that the nucleation has to happen first to form a stable nucleus, followed by the growth of that stable nucleus, the rate equation for that is the Johnson-Mehl-Avrami equation, which is 1 minus E to the minus pi nucleation rate, crystal growth rate cubed, time to the 4th power over 3. And if you are in the limit of a small volume fraction of crystals, you can do a Taylor series expansion of this exponential for a small time and just keep the linear term here. And then this gives you that the volume fraction of crystallization is approximately equal to the argument here of this exponential. So 1/3 times pi times the nucleation rate I times the crystal growth rate U cubed times time to the 4th power. And this equation is valid for a small amount of crystallization under isothermal conditions. And what we can do is use that expression to map out what's called a time temperature transformation diagram, or a TTT diagram. And what this tells you is it gives you contours for what would be a constant volume fraction of crystallization for heat treatments at a given temperature for a given time. So with this time temperature transformation, or TTT diagram, temperature is on the y-axis, time is on the x-axis, and then transformation is given by the contours on this plot, which correspond to constant values of x, or constant values of the volume fraction of crystallization. And a typical threshold for what constitutes a glass is often given by x equals 1 part per million, or x equals 10 to the minus 6. This is a typical instrumental limit for being able to detect crystallization. So the assumption here is that if x is less than 10 to the minus 6, that's less than 1 part per million crystals in the system, we would consider that to be a glass. However, if a greater amount of crystals form, then it's not purely a glass. It would be a glass with embedded crystals, which we could call a glass ceramic. And that's what we're going to come back to 2 lectures from now as part of chapter 4. Now, the nice thing about these TTD diagrams is that they can define the critical cooling rate to achieve a certain volume fraction of crystallization. So, for example, if you take a contour that corresponds to the desired level of crystallization, maybe the contour that corresponds to 10 to the minus 6, that gives a contour that looks like this. And there's going to be, if you draw a tangent line between the melting temperature where you start cooling the system at 0 time. So if you're at the melting temperature at 0 time, and then draw a straight line, so it just barely touches this contour that corresponds to the desired volume fraction of crystals, that straight line here tells you how fast that you need to cool the system in order to achieve that level of crystallization. So the slope here tells you how fast you need to lower the temperature over a given time. And this is what's called the critical cooling rate to achieve a glass. So if you've got a critical cooling rate of, say, maybe negative 100 degrees Celsius per second, that means that you need to cool the system at least 100 degrees Celsius per second in order to get a glass. And the contours here will shift to the left or the right depending upon the volume fraction of crystallization. If you've got a higher value of x, that corresponds to shifting this contour to the right because it takes more time for a greater volume fraction of crystals to form. If you've got a lower value of x, a lower value of this volume fraction of crystallization, that corresponds to this contour being shifted to the left, and that means that a faster critical cooling rate is required to achieve that lower level of crystallization. So this now completes chapter 3 in the book. To summarize, crystallization proceeds by 2 steps. First, nucleation and then crystal growth. There are 2 barriers that have to be overcome according to classical nucleation theory. Those are the thermodynamic and the kinetic barriers. Nucleation can be either homogeneous or heterogeneous, and the Johnson-Mehl-Avrami equation combines the overall rates of nucleation and crystal growth and can be used to define critical cooling rates to form a glass from the liquid state using the time temperature transformation diagram. Next time, we are moving on to the next chapter, which is chapter 4 on liquid-liquid phase separation. All right, everyone, thank you for watching, and let me know if you've got any questions.